Today we are going to talk about composite materials. So we now have a fair knowledge of metals, ceramics and polymers. So with that background, now we can develop composite materials, which is actually a mixing of all these various types of systems. So what we are planning to cover today are composite definition of composite materials and a bit of history, a bit of evolution from where these composite materials have actually this whole journey have started and where are we today, and also we will talk about the composite classification today. So first about that, what is a composite material? Now it is basically, as the name suggests, that it is indeed a mixture of two or more materials. It can be natural materials or it can be artificial materials. But the point is that when these two materials you are mixing them together, they are to be mixed such that they remain their phases as distinct phases or constituents. That means they should not chemically react with each other and form a third compound. Then, for example, that's how you can say the alloys are not composites, because in the alloys there are definitely a new material compound that gets formed out of it. A new chemical formulation comes because there is a reaction that takes place at the atomic levels. But in composites that does not happen. The two materials gets mixed with each other very intimately and a mechanical bonding takes place between the two, and that is good enough to create certain favorable properties in the material. So the mixtures may consist of metals, polymers or ceramics. It can be between metals and ceramics, some types of composites, polymers or ceramics, or metals and polymer is of course very rare, but that's also possible, or polymers and ceramics and ceramics. So various types of such compositions are possible. Now what is the primary engineering goal? Why are we mixing? We are mixing to achieve a better balance of properties from the combination of these materials. Okay, a better improvement in terms of properties. What improvements you can think of when you can think of mechanical applications? Suppose the whole system must have better strength or better stiffness or better thermal conductivity or better moisture against moisture, the expansion would be lower, so better kind of resistance to moisture, things like that. So various this type of properties you can actually achieve by making a composite. Here is an example. For example, this this is an aircraft, and you look at it that how many different places at the aircraft today composites are used. Say for example, as you can see that the red part, carbon Nomex sandwich, that is used here in the radar part, that is also here in the back side of the wings, you can see they are used. They are also used in the engine portions. So there are many portions where the carbon Nomex sandwich is used. Okay, then if you look at it, the Kevlar Nomex sandwich, that's the green part, is used in the fuselage, it's used in the tip, it's used in the tip of that the wings and the front part of the radar and the back side. Similarly, if you look at the fiberglass Nomex sandwich, the yellow part, that is also used in some of the sections. In fact, that's of course a low performance one, hence it is not used much, but that is also getting increasingly used. So thus you can see all these composites at various places, they are used in today's aircraft. As much as in some of the aircrafts, as much as 60% of the aircraft structure is replaced by composite materials. What are the domain of these composites? So I told you that it's a domain of mixing of polymers, metals and ceramics. So that means all these domains, interaction domains, they are all the composite domains. Okay, and in the composite generally you will find that there are two different phases. One phase which is more in terms of volume, we call it the matrix phase. It actually holds the entire system integrity it maintains, and the other phase are the interphases which are like reinforcement. Okay, so the other phase, let us call it the more name, the formal technical name is reinforcements. So these reinforcements have interfaces with the matrices, and that interface is to be designed in such a manner that there is no discontinuation or no debonding between the reinforcement and the matrix. If that happens, then the purpose of the composite will be defeated. If you look at the history of the composites, we can claim that it is our country who are the doyen in terms of development of composite materials, because something like 3 to 4000 BC Indus Valley civilization, you would see the first application of reinforced composites, which is in the form of straw plus mud brick. That means the clay, which is like ceramics, it acted as the matrix, and the straws, which is like a natural fiber, acted as the reinforcement. So the straw reinforced bricks, they were so much better in comparison to, if you look at the bricks at that time in the Mesopotamian civilization and other civilizations, that even today you would see in Mohenjo-daro and Harappas and all such places the evidences of beautiful structures which are made of the straw reinforced bricks. And the secret behind this strength is that the straw as a reinforcement, it works beautifully. It adds strength and it adds other properties like thermal insulations, okay, moisture preventions, etc. So to the brick system, and hence this is one of the best examples of the composites that was developed in the you can say in the very beginning of the civilization. Another interesting example of the composite is this the samurai's steel composites, which is of course used for the famous samurai swords. So there the steel composites, which is you may say that's the beginning of something like cast iron kind of things, but they are also, they have two different types of metals or metallic systems which are actually bonded together through heating and beating procedure. At a later stage, we have, as an industrial revolution, two great products of composites we got. One is the concrete and another is the cast iron. Both of them became actually revolutionized post-industrial revolution. Now then, there are many modern composites. Okay, so concrete or cast iron are composites, but if you look at their reinforcements, they are not like a continuous reinforcements. They are more like particle extensions of particular reinforcements. On the other hand, the modern composites, which are like fiber reinforced composites, they are the truly speaking the composites which have all the very good properties of a composite. For example, the tailorability is one property that you may not find in the concrete or cast iron, but you get a very high degree of tailorability in these modern fiber reinforced composites. So what are the examples of natural composites around us? There are at least two very good examples. One you carry within yourself, that is the bone. Okay, so the bone has the organic fibers and the inorganic crystals, waters and fats. In fact, if you look at a bone structure, you will find that you have the collagen fiber. So, okay, so collagen fiber is very important because once again the structure of the collagen fiber was actually discovered in India, okay, by Professor Ramchandran. So collagen fiber, and the matrix is hydroxyapatite matrix. These together has formed the bone structure. Okay. So that is a composite that you carry with you. The other one is the wood itself. If you look at any wood, you will see that it has a lignin matrix, okay, and it has cellulose or hemicellulose which are wound in a spiral form, so making once again it as a candidate composite material. So you see, nature is very intelligent to begin with itself, because most of the structural elements like wood for the tree or bone for the animals are made of composite materials. I told you that cast iron is a composite material. Why is it so? Because if you look at cast iron, as you can see from these SCM images, you would see that there are actually graphite flakes or graphite nodules in the cast iron, and that's what makes it a composite, because it is like a particle reinforced composite material. So let us divide the composites then into three parts. One part is the particle reinforced part, and this particle reinforcement could be large particle, something like concrete, okay, or could be dispersion strengthened, something like nano composites, where the particles are so small that you need special measures to actually disperse them inside the material, inside the matrix, and you get wonderful results out of it. The other types of composites are fiber reinforced composites. Various fibers, you put them in a matrix and to obtain a composite. And of course there are structural composites. Now structural composites, there are certain things that is there in it. The first point is that structural composites are developed layer by layer. Okay, so there is, it's like each single page or paper, and you are stacking all of them together. Now in each one of these paper, we will call it as a lamina. So if you look at each one of these lamina, suppose in the lamina there are going to be at least two phases. So this is a lamina. What are these two phases? You are going to see the reinforcements inside the lamina. So these are actually reinforcements, and you are going to see the rest part, which is nothing but the matrix. So there are matrix which actually holds the reinforcements, and then the two combinations, you are getting the lamina. Now when you are making the lamina, the direction, or so to say the orientation of the reinforcement, actually makes a lot in terms of changing the properties of the system. For example, you consider a beam, okay. So this is a beam, and suppose this beam consists of three different lamina. So I have three different lamina. Now if I cut the first layer and if I look at it, okay, so this is the x direction, longitudinal direction, this is the y direction. So I am cutting the first layer and looking at it. I may find that, so this is my x direction and this is my y direction. I may find that all the reinforcements are parallel to the x direction. So this is one type of a orientation of the fiber. If I look at the second part or the third part, suppose I cut it here and I look at it, I may find that all the fibers are actually perpendicular. So here the angle of the ply, so that means here the angle theta equals to 0 degree, because with respect to the x axis or the longitudinal axis, the angle of the reinforcement orientation is 0 degree, whereas here with respect to the x axis, this is 90 degree, and hence this is this is like a 90-degree ply, and I can have thus 0 degree, 90 degree, or anything in between, 30-degree plies or 45-degree plies, etc., etc. I can have various types of such plies, and that's what I have shown here in terms of the ply angles. And all these plies, you stack them together and you are going to get something from the lamina, which we will call as the laminate. That's what is a structural composite. Why are we doing like that? Okay, why are we keeping one at 0 degree, one at 90 degree, etc.? There must be a reason for it. The reason is, you see, that the lamina is highly anisotropic in nature. Now, generally reinforcements provide the the high elastic modulus, because they are having higher modulus of elasticity. So, if you have a 0 degree ply, you are going to get high modulus of elasticity in the x direction. If you make one 90-degree ply, you are going to get high modulus of elasticity in the y direction. If you take any angle ply, you are going to get high modulus of elasticity in that direction. So, what will happen, that when a load comes on the structure, if the load is in the x direction, the x direction plies take care of it. If the load is transverse this manner, then the y direction plies take care of it. If the load is angular, then this angular plies take care of it. So, that means you have provisions to take care of the loading from any direction. In fact, if your application has certain preferable direction of loading, you can keep all the plies preferably oriented towards that direction. That tailorability exists in composites, and that's the beauty of the composite structures. Now, let's talk about the particle reinforced composites. So, I told you that there are two types of particle reinforced composites: the large particle composites, which are like concrete, for example, okay, which is composed of cement as the matrix and sand and gravel. The particulate phase is harder and stiffer than the matrix, and the reinforcing particles tend to restrain movement of the matrix phase in the vicinity of each particle. Matrix transfer function transfer fraction of the applied load to these particles. So, thus you get overall strength in the system, that the stones that you use they give the improved strength, whereas the cement works like a binder in the system. So, that is the large particle. How about the dispersion strength ones? These are, like I told you, something like nano composites. Here particles are very, very small, something like 10 to 100 nanometer, and here the strengthening occurs on the atomic or molecular level. The matrix bears the major portion of the applied load, while the small dispersed particles hinder the motion of the dislocations. So, thus plastic deformation is restricted because the dislocation movement is hindered, and this yield a good improvement in the tensile strength as well as the hardness improves. So, one of the example is the sintered aluminum powder and flakes of aluminum coated with Al2O3. These are dispersed within an aluminum metal matrix to get a ceramic metal composites or CMCs. So, this is one of the example of dispersion strength composite. Now, how about the fiber reinforced composites? Here, as you know, the dispersed phase are the fibers, and then you have the matrix phase in it. So, what are the role of these fibers? You are getting better stiffness, it is stronger, you are getting better strength, and it also works like a crack bridging. So, if a crack wants to propagate, then it will, even if it propagates, each one of these fibers work like bridges, because they will not give up so easily. So, they will work like a crack bridge, and it enhances the thermal resistance of the system. Now, there are three types of fibers. Some fibers are actually little bit of extension of particles, we will call them whiskers. They are actually very thin single crystals that have large L/D ratio and has the form of a fiber, and they are flaw free and thus they are of extremely high strength but expensive. This include graphite, silicon carbide, silicon nitride, aluminum oxide, etc. And then you get fibers which has a L/D ratio equal to about 10:1, and they are either polycrystalline or amorphous. Generally they are polymer and sometimes they are ceramics. Then there are relatively larger diameters which are wares, typically like steel, molybdenum and tungsten. Tungsten particularly is used with boron as a coating layer, and that was used in the space shuttles. Now, what is the role of the matrix space? First thing, with the fiber you cannot develop a structure, so you need something to develop the structural integrity. So matrix works for binding the fibers together. Also, it protects the individual fibers from damage by external environment, and it acts as a medium to transmit and distribute externally applied stresses to fibers, and it serves as a barrier to crack propagation. So it has lot of roles. Matrix not only it helps the fibers, but also it it itself works as a barrier to crack propagation. In many cases, it's a matrix that gives actually, because the fibers fail all of a sudden. If you look at the fiber and the matrix, the fibers, the stress strain diagram, the fibers fail all of a sudden. It's like a brittle material, whereas the matrix has a typical large plastic strain it can take, is very ductile, and hence the matrix holds the system for some time. It gives you some warning. So that's the good part of it. So matrix material are generally very ductile. Elastic modulus of the fiber are generally much higher than that of the matrix, and there should be adequate bonding between matrix and fibers, okay? Because sometimes what happens is, suppose you have a fiber, you have two fibers, and if you look at it very closely, you may see some pockets of areas where there is no matrix that has reached. This happens either when the fiber spacing is very low, so this is very low, or it happens due to the nature of the matrix that it cannot wet the fiber surface. So the contact angle, okay, matters in that case. In both the cases, there will be debonding, and as a result the strength of the composite will actually drastically come down. So this is the stress strain curve. Just now I was telling you that the fiber is very brittle, so that is what is its stress strain curve. You can see one straight line and snap, okay. On the other hand, the matrix is very ductile, so it actually continues for a good amount of time, okay. So if this one may be something like 0.1% epsilon f star, this is something like 10% to 20%. So that gives us a qualitative idea. So where is composite? Composite is then in between, depending on how much of fiber is there. Composite is in between, okay. So that's the good part of it, and that's how the failure strengths in composite can be little better. And also, anyway, you cannot have a system only with the fiber, because if you have that, then there will not be any load transfer and the fibers will not be protected. So matrix protects the fibers. Now the most important thing then are three important things in fiber matrix composites, that is the fiber volume fraction, which is the ratio of the volume of the fiber to the volume of the composite, Vf. So this is fiber volume fraction. Then Vm, which is Vm over Vc, and Vv voids, which is Vv over Vc. So naturally, if I add all of them together, so what I am going to get? Vf plus Vm plus Vv equals to Vf plus Vm plus Vv over Vc. Now Vf plus Vm plus Vv is nothing but Vc. So that is why Vc over Vc is unity. So we can say that all the three things together is actually unity. If suppose there is no void, suppose if we assume such systems are there where it is perfectly voidless system, then it will be Vf plus Vm equals to unity. This is a special case. This is void free composite. Okay. In some of the cases we will assume it to be almost like void free. So we will derive rest of the things based on that. Now if you look at the weight fraction, then that is actually Wf over Wc, Wf, and Wm is Wm over Wc. Now void has no weight, so which means that for weight fraction Wf plus Wm equals to unity, unlike the weight of the volume of the voids which you have to consider. Now if I look at the density is what? W over V, and this W, the Wc for the composite is Wf plus Wm. So what is Wc? It is rho c times Vc, where rho c is the density and of the composite and Vc is the volume of the composite, and that equals to rho f Vf plus rho m Vm. So the composite density rho c is actually rho f Vf over Vc plus rho m Vm over Vc. We can write it shortly as rho f Vf plus rho m Vm. This Vf is the volume fraction Vf and volume fraction Vm. Okay. This basic rule is also known as the rule of mixtures. That means I can write that rho of a composite is actually sigma I equals to 1 to n. Okay, suppose there are n different phases there, then rho I and Vi. Okay, and this is not only valid for density but for many transport properties of a composite. Let's say the moisture absorption capability, we will call it beta C. Okay, that also is the same rule, that sigma I equals to 1 to n, okay, beta I Vi. And similarly the thermal conductivity alpha C, exactly the same rule, alpha C sigma of the composite, sigma I equals to 1 to n alpha I Vi. So thus this is a general name of rule of mixture is there for the density and such other transport properties. Some properties are not transport properties. Okay, so like strength and stiffness, for them there are special formula. For example, if I consider the longitudinal modulus, then if you assume perfect bonding between fiber and the matrix, then the strain in the fiber equals to the strain in the matrix, that is strain in the composite. In this case, longitudinal modulus, you are having fibers and matrix as if they are two different springs which are in parallel. So something like, I can show it to you through this particular example, that like you consider that there are, this spring is for the fiber and this spring is for the composite. So if I apply the load, what I am going to see that the entire load is actually shared between the two springs. Okay, so the two springs are sharing the load, one is the fiber and another is the matrix. If we look at the similar analogy, you can consider that as if you have a fiber as a spring and a matrix as another spring. Okay, and this is a parallel model for longitudinal modulus. And if I am applying the load, so I am applying the load on the system and the load is shared by the two, but in terms of the strain, the same strain you are going to see in the matrix as well as the fiber. Okay, so that's what is the assumption in this case. Okay, so we can say here that the epsilon f is equals to epsilon m equals to epsilon c, and the load is shared between the two, that is, so PCPF plus P matrix. Okay, so this is how the load is shared between the two. Now in terms of the stress, if I want to define each one of these loads, how do I do it? PC is nothing but PAF is nothing but you can call it to be sigma f AF. Okay, and sigma f is actually EF epsilon f, and since epsilon f equals to epsilon c, so you can also write it as EF epsilon c. Similarly, PM is, so this is PF sigma f AF, and that is the sigma F is denoted by this one, right, EF epsilon C. Similarly, Pm is sigma m m, and where sigma m is Em epsilon m, please correct it, and that is nothing but Em epsilon C. So then and your Pc is nothing but sigma C epsilon C. So if I work on this whole thing, so where do we reach? We see that sigma C AC is sigma F AF plus sigma m m, which means sigma C is sigma F AF by AC plus sigma m m by AC, and since you are considering the cross sectional area and you consider a unit thickness of the system, so in this direction, okay, so consider a unit thickness, so this is unity, then AC you can say it to be AF plus AM, and that is nothing but VF and VM. So hence sigma C is sigma F VF plus sigma M PM. So interestingly, this is also following the rule of mixture, but because of a different reason, because of the load share, okay. And similarly, if you actually put this epsilon C in the terms of the strain, you will see the EC longitudinal also follows the rule of mixture as EF VF plus EM VM. So that is in the longitudinal direction. What happens in the transverse modulus? Transverse modulus, the load is now coming first to the fiber, suppose, then to the in between matrices. So that means as if there are two springs, one is the fiber spring and another is the matrix spring, and the load is getting transmitted. So unlike the other case where they were sharing, here the same load is actually getting passed, something like this, okay. So something like you have one as the fiber, one as the matrix. As you are applying the load, the same load is passing through both the fiber and the matrix. It is not shared, but the same load is going. Now you can see that this system is more flexible, right? So no wonder that the transverse modulus is actually much smaller in comparison to this this system, which is the same type of spring stiffness, but it is much stiffer. So in this particular case, as you can see that the tensile load is acting normal to the fiber direction. Since the same load is passing, so the stress is same now, sigma F equals to sigma M equals to sigma C. In this particular case, you can write that sigma C over EC is sigma F over EF PF plus sigma M over EM, and since sigma F equals to sigma M equals to sigma C, so I can cancel all of them. So what I get is 1 over EC equals to VF over EF plus VM over EM. In other words, EC here is EF EM over EF VM plus EM VF, okay, or you can also write is using this particular relationship, okay. So that is the composite modulus in the transverse direction. So this is where we will complete our lecture. In the next lecture, we will talk about application of fiber reinforced composites. We will talk about some of the polymer matrix, some of the metal matrix, and some of the ceramic matrix composites. Thank you.